In this video, we're going to talk some more about the game Catan. In a previous video, I described the game and how it's played a little bit, and I also talked about the experiences with playing with the pair of dice, the Catan dice, versus playing with the deck of cards, the special Catan deck called the event deck or the event cards. Different experiences. Now, in this video, though, we're just going to focus on the dice. So I had this idea a while back. I thought it might be a fun little practical joke to play on my family if I came in with a drill. I found a drill that was the exact right size so I could just carefully drill out that pip, that one pip on the one side, and find a bearing or something, some kind of a BB bearing kind of thing that's the exact right size. So when I drill this out, I can drop that in there and then use some kind of like maybe an epoxy or glue or some kind of filler and just make that pip look exactly the same as it does on the dice right here. Paint it yellow. Do the same thing for the yellow dice or die and have a pair of loaded dice for Catan. And keep it a secret. Not tell my family. So this was the distribution that we expected when the dice were fair. And we knew this because we can look at combinatorics. We can look at combinations. So the nice thing about assuming the dice are fair is that if they are fair, I know what the distribution of the numbers is going to look like. This is it. On the other hand, if the dice is loaded, if we're dealing with loaded dice, the higher numbers are going to come up more often, but how much more often isn't really easy to figure out. It's easy to figure out the distribution of fair dice because that's a math thing. That's an assumption. The dice are fair. We know what it looks like because we can just look at combinations. But when we have some sides of the dice coming up more frequently than the others, what that exact distribution looks like is not entirely clear. So this distribution I created, I made it up. I thought, well, maybe it looks like this. This is kind of the idea. And the other thing I want to mention is I've switched this up to relative frequency. Now we're looking at the vertical axis as percentages. So rather than, and again, we could convert the frequencies in the previous fair dice plot to relative frequencies, which I do later in this presentation. But this is just a little bit of an easier way to create such a graph for the bias dice especially. So if we're going to, one of the ideas here is, and again, I'm kind of making up a narrative or a story to go along with this, but I can see, I can imagine if I actually did do this and started playing the game, that, and of course, I would strategically locate my pieces towards the higher numbered hexagons, knowing that the dice are going to produce those higher numbers. Of course, nobody else in my family would have that information, so they would follow their normal strategies. Usually that's placing your pieces close to the numbers that come up more frequently on fair dice. So maybe in playing this game with my special dice along the way at some point, my youngest son says, "Dad, I'm not buying this anymore. This is the luck has turned. I'm not lucky like I used to be, or you're getting too lucky now. I think there's something wrong with these dice." Well, I might suggest that we do some statistics to investigate. How would that work? Well, that's going to be the point of the video. And it's interesting because, essentially, my son would be accusing me of cheating. Of course, we know the truth, as do most, of course, people that are accused of crimes generally, I think, probably do know if they did it or not. Yet we go through this, really important process to decide whether the person is telling the truth or not. So we could replicate that with the dice. Now, a statistical hypothesis is always in two parts. The first statement is what we call the null hypothesis. And we use the notation H sub 0 with a colon, and we can write a statement. And if you got into a more advanced statistics class, these would have equalities and inequalities and look a lot more mathematical. But I'm really approaching this from a very conceptual point of view. It's important to me that you understand the concepts, the flavor of how this works, rather than all the technical details. But in any case, always when we create a statistical hypothesis, we do it in two parts. We have the null hypothesis, dad's innocent, and we have the alternative hypothesis, which is the dice are loaded. And notice these statements are what we call dichotomous. The dice are fair or they're loaded. Dad either didn't do anything with the dice, they're fair dice, they're what came with the game, or wait a minute, something's up with these dice. That would be the alternative. So that one of those two things in statistics, when we do statistics, we create a hypothesis in this way. One of these two things are true, the other, and if one is false, it rules the other out. So in other words, the way statistical hypothesis testing works is if we decide that the dice are not fair, we reject the null hypothesis, and that leaves only one conclusion, that the dice are loaded. And that's how statistical hypothesis testing works. Now, what we would do is we would do an experiment. We would roll the dice, say. And from that experiment, we would get data. The data values of 12 here. So suppose I took those dice, I rolled them, boom, the 12 came up. Now, of course, I would know that the dice are loaded, and I look at the 12 and go, yeah, not surprising. But the statistician wouldn't know that. The statistician wouldn't know that. My family wouldn't know that. They would just look at that data and they would wonder, what should we conclude from that? Statistics gives us a philosophical framework to think about data like this. What should we conclude from this? And in statistics, what we do is we calculate something called a p-value. And the p-value is I believe the p-value in statistics is probably one of the most misunderstood and most misinterpreted numbers or ideas in all of statistics. And for good reason. It's a very complicated idea. Now, I want to put some more pieces into place before we get to the actual calculation, which in this example will not require a whole lot of mathematics, which is good. That's why I like the example. Heavy on concepts and philosophy, really light on how you would do the calculation. A lot of times in statistics, to calculate things like p-value, it's really a calculus problem. But we're not going to talk about that at this moment. But in any case, this particular example, we won't need any calculus for. So one of the ideas, in order to think about how to calculate the p-value, I have to think about what direction would be considered extreme. In other words, I know because I loaded the dice that I would see more sixes, but I don't know that my family would suspect that. So they may say, well, okay, the dice could be biased to the right, which means they're going to be producing higher numbers more frequently, or it could be biased to the left, which means that the dice will be producing lower numbers more frequently. So, we kind of have to work through this and think about it. There's a couple of different ways we can approach this. And again, it depends on how we structure that alternate hypothesis. I'm going to keep things a little bit simpler in this video. And I'm just going to assume that, I know that the one's drilled out, and it's possible that people that, my family might say, well, if dad did something to the dice, probably it would be that one side there because that's the easiest to deal with. And so we're going to just think about this narrower statistical hypothesis. We're going to assume that if the dice are biased, they're biased towards more sixes. That modifies our statistical hypothesis a little bit. We still assume in the null that the dice are fair, but in the alternate now, we're going to be specific and say the dice are loaded towards the sixes. Now again, we're going back to review. Here's that frequency plot for the null distribution where I'm using the relative frequencies now instead of stacking the x's up. So we're looking at percentages. So the 2 happens about 2.8% of the time. The 7 happens about 16 plus percent of the time, and so forth. So it has the same shape. It's really the same distribution. It's just in how we're interpreting the frequencies, whether we're looking at them as percentages or as counts. And then the alternate hypothesis, we're going to say the shape is going to look more like this. Exactly how that distribution for the alternate looks, that's not clear. But, and I made this up, this is hypothetical, but it would look something like this if the alternate was true. Because we'd be seeing more 6s, we'd be seeing higher numbers more frequently. Now, direction of extreme. In this case, we say the direction of extreme is one-sided to the right. And the reason for that is because as the numbers get bigger, the null distribution says they should get less frequent. Those numbers should occur less frequently. So on a fair dice, 10s, 11s, and 12s, as you move to the right, those rolls get more and more unusual. At the same time, though, if the alternate were true, those rolls would be more common. They would be more common on a loaded dice, like a 10, 11, or a 12 would be more common on a loaded dice than it would be on a fair dice. And so that's why we say that the direction of extreme is one-sided to the right. And that makes a difference when we actually calculate the p-value. So again, coming back to this p-value, here's the definition. This is very much a simplified definition. This is how I like to think about the p-value. Now, if a mathematician or a statistician or a mathematical statistician looked at this, they might say, well, Todd doesn't have the right definition here. This isn't correct. And it's very simplified. But I think it gives the right idea. So here's the definition in this context. We're going to say the p-value is the chance, given that the null hypothesis is true, of sampling our data. Now, again, it gets more complicated than that, but for now, I want everyone to just think about that. It's what we call a conditional probability. We can think of this as the probability of rolling a 12 if the dice are fair. What's the probability of rolling a 12 if the dice are fair? Now, generally speaking, to calculate a p-value, we need these 3 things. We need to know the null distribution. We need to know the direction of extreme. And then we need some kind of a test statistic, some kind of a piece of data. Could be a sample mean, could be a sample proportion, lots of different things. But in this case, it's what is the roll? What's the sum of those pips when you roll 2 dice? That's our data in this example. Now, there's a reason why we look at this. There's a reason why we look at it this way. We need the null distribution because to calculate the p-value, we're assuming the null hypothesis is the one that's true. That is a real advantageous thing because I actually can say mathematically, I can write that distribution down and calculate probabilities. I can say, what is the probability of rolling a 12 on a fair dice? That's about 2.8%. If the dice are loaded, what's the probability? Well, I don't have that distribution. This is the distribution I have because it's based on an assumption that the dice are fair. Dice are fair, and it's a combinatorics problem. How many combinations, can happen? So there's one way to roll a 12 out of 36 possibilities. So in this case, the p-value would be 136. That's about 2.8%. So how would we interpret what this p-value means? Well, what we need to really think about is what's called a type 1 error in this context. A type 1 error means we reject a true null hypothesis. In this case, it would mean that we reject the assumption the dice are fair and we decide to believe the dice are loaded and, Dad's a cheater and all this and that. And so that takes us to these consequences. So if a type 1 error is made, what it means is the dice are fair, are actually fair, but we concluded they're loaded. It was that one time out of 36 that 12 came up on fair dice, and we thought, man, that's just too unlikely. We're going to reject that hypothesis and conclude that the dice are loaded when they're really fair. So really know how to evaluate the p-value. I think you really have to think about what the consequences of a type 1 error are, because they're not always going to be the same. It's very contextual. If we're talking about playing craps in a casino and the house, the pit boss at the table suspects that the dice are loaded, they're just going to grab the dice and throw them away and put a new set of dice out there. The consequences in that context, really no big deal. Dice aren't that expensive, especially when thousands of dollars are being gambled with. So that, worrying about a type 1 error when you're playing craps in a casino, when they especially from the house's point of view, when they only really need the dice to be fair, they're going to win in the long run. Not really that big of a consequence of a type 1 error. But I think if we think about it in terms of accusing somebody of being a cheater or something, that's a different kind of a consequence. That's a more severe consequence. Now, the way this works is, if the consequences are really not that severe, then the p-value can be a fairly large number. Because again, it's not that big of a deal if we make a type 1 error, if we reject the null and it's actually true. But on the other hand, maybe accusing somebody of cheating is and they're actually not. So I mean, a type 1 error would mean you're accusing somebody of cheating and they're not cheating. We may want a smaller p-value in that situation where the chances of that happening are much lower. And I could give an example, like, if we're talking about a person that's accused of a crime, the jury's instructed to assume that person's innocent. Of course, the alternative would be they're guilty. A type 1 error in that context would be to reject the assumption that the person's innocent, to reject that null hypothesis in favor of guilt. And the type 1 error would mean they were actually innocent in the first place. That is a severe consequence. That is a situation where an innocent person goes to jail, is punished, fined. So those consequences are severe. So the biggest point I'm trying to make here is that how we interpret the p-value really is contextual. It's based on how severe a type 1 error would be, the consequence of a type 1 error would be. So there's no hard and dry answer here. I mean, there's no cut and dry answer. There's no, in statistics, there's no way to prove anything. Are the dice fair? Maybe, maybe not. We know the p-value here is about 2.8%. I can tell you the standard for p-values in research and science that for the last several decades has been, if the p-value is less than 5%, we should call that a significant result. In other words, in statistics, we use this word significant. It's very important to think about that too. When you read statistical research, you should never see the authors talking about, well, our data proves that the null alternate hypothesis is true. That's just not how statistical decision making works. There's always the possibility that our decision is made in error. The smaller the p-value, the less likely that is. I have to be a little bit careful here too. I mean, again, when you read the Bigfoot essay I wrote, the essay about Bigfoot and statistics, it's a little bit of a different situation there. This is a very nice example because we're rolling dice, and what happens with the dice, if they're fair, is very much something that can be modeled. With the Bigfoot example, I'm talking about the existence of a mythological creature. And what I'm using for data is the length of a footprint. Now we can calculate a p-value for the Bigfoot example and say a human with a foot that big is rare and unusual. And we could rule out, even using statistics, that that print was left by a human. But it's still a stretch to get to, we're going to reject the assumption that Bigfoot does not exist in favor of Bigfoot does exist. So again, statistics can be very complicated. It can be very, what's the word I want to use? It can be very abstract, and it can also be very misleading. And it's very important when we're analyzing statistics to keep our eye on what is that variable that's actually being measured and how well does that connect to the actual hypothesis. In the dice example, we're looking at the numbers that are rolled on the dice. It's very, very straightforward. We know what we should expect to see with the numbers if the dice are fair. We roll them one time, we see what happens, and we take that information and calculate p-values that relate directly to whether or not the dice are fair or biased. Not so much so with the Bigfoot example. So getting back to this example, rejecting the null hypothesis based on this particular p-value means that there's about a 2.8% chance that we're making a type 1 error. That's not a really big chance. And the interesting thing is, in this example, there would be no type 1 error because I've already admitted that the dice were tampered with. They are loaded dice. So the statistics would have actually identified that in this particular example. The tricky part for the statistician, though, is, and it's the same thing, I think, with the justice system, you don't actually ever know for sure if the person's innocent or guilty, I don't think. I mean, I could even use the example of the O.J. Simpson murder trial way back in the 90s, or was it the 80s? Goodness, I forget now. It might have been the 80s. In any case, O.J. Simpson knows whether he did the crime or not. I don't know. I will say, I don't know. I have an opinion based on what's happened and based on the evidence, but I don't know. Same thing's true here. We can have an opinion that the dice are loaded, but if I don't admit the truth, then my family wouldn't really know for sure. What they would know is that it's really unlikely to see a 12 pop up on these dice. Therefore, that's evidence something's going on. But it doesn't prove anything. This example fits very nicely, I think, with the bag A, bag B, the problems that in the assigned reading. And I'm going to let you go ahead and read that for now, and then I'll come back and talk about that some more. So I hope this video has helped shed some light on these ideas. Please send me a message if you have any questions, and have a great day.